Okay, guys, how's everybody doing? Professor Bryant back, another installment of Workout Wednesday, continuing with nuclear chemistry. This time we wanted to focus on a binding energy problem utilizing the mass of a particular nuclide. And we'll go back to the text. And we're looking at question 21.47 asks us how much energy must be supplied to break a single aluminum 27 nucleus. Very important, distinguished meant here single nucleus into separated protons and neutrons if the atom has a mass of 26.981536 AMU, and how much energy is required for 100 grams. They tell us that the mass of the electron is on the inside back cover. Now remember, we have, and I have given you the fundamental constants in your reference material. So for any problem that involves you needing the values of the mass of electron, neutron, and protons, those are going to be given to you on a sheet like this for your assessment. Okay, so where do we start? Well, since they have given us a particular nuclide, and that is aluminum 27, and they have given us the mass of that as determined by scientists over the course of the last couple of years. What we need to do to find the binding energy is to find the mass defect, to find the change in mass that came from the formation of this particular atom. And that involves doing the mathematics of adding up what the atomic mass should be based upon number of protons, neutrons, electrons. Where do we get 13 protons from? That will be from the periodic table, aluminum's atomic number. 14 neutrons is based on the mass number, and 13 electrons is the ground state atom has a total valence electrons of 13. So we do the mathematics here, just simple basic addition to get the mass that we expect it to be. And that has been done here via calculator. And we see that it is a larger value than this, which is what we expect, right? We expect that the atom, once come together, should be lesser than the separate parts. And that in itself is called the mass defect, right? So we are calculating mass defect here, which we can show as delta M. And you can call this mass defect. And that delta M is 2.414958 times 10 to the negative 1 AMU. I would say at minimum 5 significant figures for the majority of these problems. Remembering that AMU is also grams per mole, and that can be converted. And they have asked us how much energy to break a single nucleus. Well, this mass defect needs to be placed to answer that question. The mass defect needs to be placed in the E equals mc squared, where delta M is our mass and c is the speed of light, which is given as a constant. One thing that we must remember is that eventually we're going to have to convert this value in grams to kilograms. Doesn't matter when you do it, just remember that you have to do it. So in this example, I went ahead and calculated it as a function of grams, and we get this value 2.173462 times 10 to the 16, a very large number, grams per meter squared, grams meter squared per second squared mole, and then I converted that to kilograms here, and remember that just changes things an order of magnitude of 3. Now we should recognize that kilograms meter squared over second squared is a joule, so this value actually gives us 2.173462 times 10 to the 13 joules per mole. And now we have a unit we can work with, right? We have an energy unit, joules, that we're familiar with, we can work with. But joules per mole is not what we have been asked for. We have been asked for a single atom. So whenever we're dealing with atoms, to get from mole to atom, right, we always need to use Avogadro's number. And to use Avogadro's number is to recognize that there are 6.02 times 10 to the 23 atoms in 1 mole. So we take some dimensional analysis that we should remember from General Chemistry 1 and convert joules per mole into joules per atom. And we end up with roughly about 3.6 times 10 to the negative 11 joule per atom of aluminum 27. So this is the first part of the question. So what you need to be able to do is take a given mass of an atom, calculate a theoretical mass of that atom, find the change in mass to the change in energy, and then convert to whatever energy units you have been asked for, per mole, per atom, millions of electron volts, whatever units you need from there. But the main part is to be able to get the mass defect and then go from there. Okay, part 2 of the question asked us how much energy is required for 100 grams of aluminum 27, right? 100 grams. So we just calculated energy per mole here. And we can then utilize energy per mole, joules per mole, to calculate per gram because we know how many grams are in a mole. So if we determine 100 grams and divide that by the atomic mass listed for aluminum, we see that we have roughly about 3.706238 moles of aluminum. And if we multiply that number by joules per mole value that we have here, then we can get the value that we're interested in, and we see that in 1 mole there's a huge amount of joules, millions, billions of joules of energy associated with the binding energy of 100 grams, right? 100 grams. So this is a great calculation question that focuses on understanding mass defect and then some energy conversions. You have to be able to convert energy values and solve for binding energy if necessary, right? You need to be able to work this problem backwards as well if necessary. Okay, again, if you have any questions, be sure to comment or send me an email.